So I'm going to talk about GPU-friendly stroke expansion today, and this is joint work with myself and Arman Uguray. We're both at Google. So what problem are we trying to solve? We're trying to render vector graphics, like SVGs. And vector graphics, the geometry in vector graphics is primarily made up of fill primitives and stroke primitives. And there are a lot of papers that have been published on how do you render filled paths on a GPU, but rendering stroke paths properly on a GPU is a harder problem, and there are fewer published techniques on this. What we're going to focus on today in terms of the rendering strategy for getting stroke paths rendered is stroke expansion. So stroke expansion basically says, take that vector path and expand it into a filled path that represents that rendered stroke. That is not the only technique that you could use. There are other techniques like local methods, which break down the stroke into triangles, and point inclusion techniques like distance fields. There's some trade-offs there. There's some real advantages to having kind of both the fills and the strokes in the same stream of paths that get rendered. So we're going to be focusing on that today. And as I say, this problem of stroke expansion hasn't really been done on GPU before. There's some tricky aspects, and so a lot of what we're going to do in this talk is go through how do we make this algorithm GPU friendly. So the core of our technique is Euler spirals, which is a well-known mathematical curve, but not commonly used in this kind of rendering pipeline. And so the general structure of our pipeline is to convert the cubic Béziers that make up those SVG paths in the vector graphics input into Euler spiral segments, and then compute the parallel curves of those Euler spiral segments, and then flatten those into either lines or arcs, add the evolutes and the joins to get fully correct stroke rendering, and do all of this work in parallel. So let's see, I think I'll go to the demo. So this is a web demo. So this is actually running on the CPU, but it's the same algorithm that we're implementing on the GPU. And you can see I'm manipulating a Bézier, a single Bézier curve segment. The offset, the width of that stroke, is one of the parameters. And the other parameter that I have here is the tolerance, because you want to adjust the tolerance. So this is in pixels. So if it's 1 pixel, it's basically saying that the filled path that it generates is within 1 pixel of the kind of true mathematical outline. Generally, you want to set that to about 1/4 of a pixel. That tends to be the threshold of where you can see it. And of course, you don't want to set it too tight, because then you generate too many primitives, and that slows down performance. So one of the other, so you can see kind of the way that the number of subdivisions tracks with the tolerance that you set. And then we can also switch between lines and arcs as the primitive. Okay, back to Keynote. Great. So this choice of line arc, we think that arc is the sweet spot for a GPU path rendering pipeline. And it's a trade-off. Obviously, arcs are a little bit more complex to render, but you get so many fewer of them to achieve the same error tolerance that I think that's going to be the better point in the trade-off. But in any case, our algorithm will lower either to lines or arcs. That's kind of one of the parameters that we have. Another feature of our algorithm is that we do correct rendering of strokes even when there's kind of extreme curvatures involved. And this is based on theory from Diego Nehab from 2020. There's a great paper. We refer to it extensively. And here you can see the comparison between weakly correct rendering on the top, where you're only using the parallel curve of the stroke to build the outline. And that's fine when your curvature is not very large, like on the left. But when you get larger curvatures, in order to get correct rendering, you have to add these evolute sections. And the Nehab paper goes into a lot of detail about what that means, how you add them to the outline, and how to compute them. And you can really see that in this animation. This is, again, a single cubic Bézier path. And you can think of the definition of stroke rendering as taking a line and sweeping it along the curve so that the orientation of the line is normal to the curve, and it should be additive. It should be building up the path. You shouldn't be carving away. And if you only render the parallel curves to form that outline, then you see parts of the stroke cut away. So adding those evolutes gives you a strongly correct rendering, a really mathematically correct rendering that's incorporating all of the elements of that stroke. Here are a number of other examples. So you see the strongly correct rendering on top and a weakly correct rendering on bottom that's only using the parallel curves that's missing some pieces. So as I say, we're using an Euler spiral as the intermediate representation of these curves. It's much more common to lower to something like a quadratic Bézier, but we think that the Euler spiral has some real advantages in this application. The definition of an Euler spiral is that the curvature, which is represented by the osculating circle, is proportional to the arc length. It's linearly proportional to the arc length. And that gives you really beautiful, simple mathematical properties that we're going to exploit as we use that to generate these stroke outlines. You can also see the evolute of an Euler spiral has also a very simple, easy to characterize mathematical, and that's the center. The evolute of a curve is essentially the center of the path taken by the center of the osculating circle. So the first stage in our pipeline is to take the input cubic Bézier segment and convert it into Euler spiral segments. So that means subdividing it. And the essence of subdividing it is to compute the error. So you need to compute that error, and if the error is within the tolerance, then you're good. But if it exceeds that tolerance, then you need to be subdividing that. How do you compute this error? So a cubic Bézier segment is characterized by 4 parameters. It's a sort of a 4-dimensional parameter space. You can think of that as endpoint tangents and also the distances of those control points. So the endpoint tangents uniquely determine what that Euler spiral is. So now you just need to determine the distance between that Euler spiral and the input cubic Bézier. And the primary term, there's 3 terms, all the details are in the paper, but the primary term, the thing that really predicts that, is the delta in area between the cubic Bézier and the Euler spiral. And I should also say, there's 2 error metrics that are involved. You're first going from the cubic Bézier to the Euler spiral, and then you're going from the parallel curve of the Euler spiral to the flattened representation. So there's a theme of error metrics. And so we need to compute this error metric. We need to determine whether the approximation is within that error tolerance. And the traditional way you do that is what we call cut then measure. So you create the approximate curve, and then you sample at multiple points along that curve and measure the error at those samples. And there's 2 problems with that. First of all, if you're sampling, you might miss something, especially if there's a cusp, especially if there's a large variation in curvature, which absolutely can happen with cubic Béziers. And the second problem is you're iterating. You're doing some iteration per sample, which is really not fast. So our approach is to compute an error metric analytically, directly from the parameters of the source curve. A good error metric is going to be easy to compute, and it's also going to be conservative as a bound on the actual error. So the error metric will always be at least as much as the true mathematical distance between the curve and its approximation. We use error metrics for 2 different steps in the pipeline, the conversion to Euler spirals and then from Euler spirals into the liner arc primitives. And for the second one, we use a technique called invertible error metrics. So the idea is that a forward error metric, you give it the subdivision and it predicts this is what the error is, but an invertible error metric lets you go in the opposite direction. Given a target, given a threshold for your error, how many subdivisions do you need? And also, where are those subdivisions? In order to do an invertible error metric, the error metric itself must be mathematically simple. You can't do some complicated formula. You need to be able to invert it. You can interpret, for the purpose of lowering an Euler spiral parallel curve to line segments or arc segments, you can interpret it as a subdivision density, like how dense is that subdivision? And for lowering the lines, that really boils down to the square root of curvature. So I'll kind of go into a little bit more detail on that. What if you want to flatten a circular arc into a polyline? The distance between that line segment and the arc segment is a simple trigonometric function. It's just it's something involving cosine here. And you can approximate that, for a small angle approximation of cosine, you can approximate that very well, and conservatively, by the way, just by using this simple formula of the curvature times the square of the arc length divided by some constant. And then if you invert that, then that predicts the number of subdivisions that's required. And placing those subdivisions is trivial because you just put them evenly spaced. So this is an extremely simple problem to solve for a circular arc. But we're not concerned with circular arcs, we're concerned with arbitrary curves. And we take that simple formula, that simple trig formula, and generalize it by computing the integral of that subdivision density over the length of the curve. So the subdivision density is essentially the square root of curvature, so we're computing the integral of that over the curve, and that's accurately predicting the area, predicting the error, and then we can go ahead and invert that as well. A little caveat, I say arbitrary curves, this only works when the curve has monotonic curvature. You need to split at curvature extrema, but that is one of the advantages of the Euler spiral as an intermediate representation. It is monotonic in curvature, so when you subdivide into Euler spiral segments, you get that split at curvature extrema kind of for free. So here's a visualization of subdivision density. The Euler spiral is in the center, the parallel curves on either side, including a cusp, and then you can see the flattening into line segments with an animated, decreasing tolerance. And you can really see the subdivision density here. And in particular, you can see that there's two places where that density is 0. One of them is at the inflection point of the Euler spiral, the place where the curvature becomes 0. And the other is at the position of the cusp. And kind of surprise that the formula for this, it's a very simple mathematical formula, and it's symmetrical. You can kind of swap where the cusp is and where the inflection point is, and it comes out the same. So the fact that this is a simple mathematical formula means that we can take the integral of that, which is what we need to do the invertible error metric, to predict where those subdivision points go. And it's a reasonably simple analytic integral to compute, and then we also have an approximation, the details are in the paper, very close approximation, we just kind of curve fit in Desmos to achieve this, and the advantage of the approximation is that we can again invert that. So all of these elements contribute towards a GPU-friendly implementation. Our goal is to implement this on the GPU so that we can obtain interactive frame rates even with very complex scenes, something like a map. So the implementation, the overall implementation on the GPU is a pipeline. The first stage is input processing, so most importantly, we have to represent that scene. We split it into 4 different streams. So there's one stream of the path tags, which tell you, is it a line, is it a curve, and also the topology. The next stream is the coordinate data for those path tags. We have another stream of transforms, which can be set independently. So you can do something like animate a transform of some of the paths in your scene without having to re-encode the whole scene. You don't have to apply the transform on the CPU. And lastly, we have another stream, which is the styles. And the style is primarily the width of the stroke, but also details like if the cap is round, or the joins or miter joins or bevel joins. So given that input processing, we do some prefix sum on that. I'll show that shortly in another slide. And then we apply the main compute shader. This is all implemented as compute shaders in WebGPU. The main compute shader is flattening, which internally is a pipeline fitting the input curves to Euler spiral segments by subdivision. Then we compute the parallel curves of those Euler spiral segments. And then we add the stroke caps and joins and take those flattened curves, arcs or lines or arcs, and output that to a line soup buffer. And this is one of the insights that we came up with. Usually when you're doing stroke expansion, you have a sequential representation that walks the path in clockwise order. But it turns out for rendering a path, you don't need that ordering. If you're doing the rendering on a GPU, then the output can be completely unordered, and we exploit that fact. The output of the flattening stage, this line soup, is then fed into a rasterization stage where we sort that line soup into tiles, and we compute the filled pixels of each of those tiles in parallel using scanline rasterization. So there's a few things that are tricky. There's a few reasons why this hasn't really been done, stroke expansion hasn't been done on the GPU. And one of them is recursion. Adaptive subdivision is fundamentally a recursive algorithm. If you have a curve segment and you say, oh, it exceeds the error tolerance, then you need to recursively apply that adaptive subdivision to each of the subdivided halves. And that's a problem. Compute shaders don't support recursion. The standard technique to convert recursion to iteration is that you represent the stack explicitly. It's not a very difficult thing, but again, that stack is potentially unbounded depending on the recursion depth, and that's also something that isn't really friendly to implement in compute shaders. So one of our insights is that for this particular problem of adaptive subdivision, you can store the entire stack state in 2 scalar words. So there's basically 1 bit in one of those words for each potential depth of that recursion. And you see the algorithm here. The path encoding, making that path encoding, when you upload those paths to the GPU, you want it to be a compact encoding, but you also want it to be efficiently processed in parallel. And the way we do that is the path, in order to be compact, the path element needs to be variable size, because if you have a cubic Bezier segment, that has a lot more coordinates on it than if you just have a line segment. So the way we do that is we have a separate stream for the path tags and the coordinates. The path tags are just 1 byte per path tag, and we map that to a size, and then we run a prefix sum over that size, and that gives you the index into the coordinate buffer of where those coordinates are. And another thing you can see here is that there's this overlap where the end point of one line segment overlaps the start point of the next curve segment. You don't have to store that twice in the representation. Results. So we, as I say, we implemented this in WebGPU, and that one of the benefits of that is that lets us deploy the algorithm on an extremely wide range of GPUs, from mobile GPUs running on Android up to high-end discrete cards. It's a little complex to characterize, to figure out exactly what you're measuring. All the details are in the paper, but the bottom line is that we are more than 10 times faster than the fastest CPU implementation of stroke expansion, easily supporting interactive frame rates. And also, as you can see from the graph here, that it scales with GPU power. There's no CPU bottleneck to this process. So what you see in the stacked bar chart is that each one of those colors represents a different scene out of the NAHAB timings data set. And then one of the other things that you see is that arcs are faster to generate than lines because there are fewer of them. Most of the time that's spent by the algorithm is actually in generating the output. So let me go now to a demo of the renderer. So this is running natively. Because it's in WebGPU, you can also run this inside Chrome. You can run this in any browser that implements WebGPU. Chrome is shipping that, and the other major browsers have it sort of in beta. So obviously, if you've got a vector graphics renderer, you have to be able to render the tiger. That's the standard scene. That includes both strokes. You can see the very thin strokes on the whiskers of the tiger here, and of course, filled regions. And then here's some of our test scenes for strokes. And you can see, among other things, the different joins and cap styles. And then we're testing the fact that this works with different transformations that are applied after stroking. Here's a set of examples of tricky strokes that have tricky curvature, et cetera, et cetera. And this is all running, on the GPU, of course. This is a sort of a curated set out of the stills data set of NAHAB. And you can see, again, correct rendering of these. Another example showing, more strokes. Here you can see some of the other primitives. We're not just doing fills and paths. We can do images. We can do text. You do see the stroke style applied to that line of text. And one of the other things you see here is completely dynamic rendering of the text, including animation of the variable font parameters. And we also have emoji, color v1 emoji rendering wired up the same way. Just sort of performance stress test. This is a huge number of stroke segments. And then this is our adaptation of the motion mark benchmark, and we can go up to, I think, probably there's the number of segments. I think we can go up to about 120,000 segments and still be inside the 60 frame a second budget, which is just tremendously faster than competitive renderers. All right. Okay, so there's a little bit more work to be done. So I think we can exploit even more parallelism. We're doing some of the operations sequentially per path. We're doing all of the path segments completely in parallel, but walking through generating the arc segments from a single Euler spiral, we're still doing that sequentially. And I think work graphs make a really interesting, I think they're a good fit that, there's this pipeline where you're breaking things down and filtering and expanding. And I think that fits into the work graph paradigm pretty well. So I'm looking forward to exploring that. The error metrics are all kind of determined empirically, and there's pretty good testing. There's randomized testing where we show that they do work, and that code is in the supplemental materials. But I also think that doing a mathematical derivation would give more insight and maybe help us fine-tune those error metrics better. One of the approaches that I'm exploring is to take the curve and expand it into a Chebyshev polynomial expansion for the Cesaro equation. I think that approach has a lot of promise. Looking forward to exploring that. One of the challenges of this technique is that you have to know how big the intermediate buffers are when you're generating this line soup intermediate buffer. You have to know how big that buffer is, and if you have an extremely complex scene, a map or scientific visualization on input, it might be non-trivial in size. And so you can, with a compute shader API, you can run some analysis and then do a read back in order to determine the size, but that's not very efficient. So one of the things I'd really like to see innovation in the GPU space is how can you make this really GPU driven or GPU autonomous, I saw as a word I really liked on that work graph poster. And then a detail that our current implementation is doing the dashing. Dashing is part of stroke style. We're currently doing that on the CPU. Moving it to the GPU, I think, is fairly straightforward. It's really just a prefix sum of the arc lengths, and we have the arc lengths. Euler spiral is parameterization. It's just you just have that arc length parameterization kind of for free. So there's some resources to follow. The landing page for the paper has a link to the paper and the code repos and so on and so forth. It also includes that interactive demo. I encourage people to play with it. It's really fun. So you can go there. The Velo renderer that this was developed for, there's an active open source project to develop that, and a number of really interesting applications being built on top of it. And then you can also follow the progress of this work on the Lanebender blog as we kind of explore more of the space. And that is my talk.
So time for Q&A.
This is really cool work. Have you, or maybe somebody else, thought about applying Euler spirals to other modeling tasks like maybe hair or streamlines for visualization or things like that?
Super good question. So the answer is absolutely yes. Euler spirals have some really powerful properties, and one of them that's very nice is that it's very easy to achieve G2 continuity with Euler spirals. I actually do go into this in some detail in my thesis. So yes, it's a primitive that people should know better, and I think one of the stories that this paper tells is I think some people are scared of them because it's a special function, it's not just a polynomial, but there are numerical techniques that you can use to evaluate and do things like Hermite interpolation and so on and so forth efficiently on a GPU. 3D is beyond the scope of this work. There is a chapter in my thesis on a generalization of Euler spirals to 3D, but it isn't something I am personally focused on.
Some other questions?
Is it like applicable to some sort of with ink diffusion?
Sorry, I didn't hear the question. Is it applicable?
Is it like applicable to some stroke with ink diffusion?
Oh, ink diffusion, right. Yes. Yes, it's a very good question. So ink diffusion, there's a couple of aspects to that. First of all, you probably want the width to be variable, whereas one of the assumptions that's being made here is that it's constant. And second, you probably want to be, having parameterized, you want to be able to go from the XY coordinates to the parameters of where you are along the strokes. I do think, I haven't built it, but I do think that these ideas would generalize to that. The fundamental problem of, if you think about computing a parallel curve, that's really a generalization of curve fitting, where that curve is defined parametrically as taking the spine of the curve and then adding an offset to it. And of course, if the offset is constant, then that gives you one curve. And there's these mathematical techniques that we can use. The parallel curve of an Euler spiral has this very straightforward closed form representation, which you would lose if you went to a variable width. But I think you can represent it as a parameterized curve that you have to apply curve fitting for. And these techniques of compute an error metric and just keep on subdividing until you get close enough to the mathematical ground truth. I do think that it could be applied. I think that's a great area for future research.
You asked for innovation in GPU compute APIs. Can you connect the dots for me a little bit and help me understand what kind of thing you might see?
The question is, I asked for innovation in GPU compute APIs. Can I help connect the dots? I have a colloquium that I did at UC Santa Cruz in April called "I Want a Good Parallel Computer." And it was recorded, but the video is not published yet. So I'm happy to show you the slides on that. And of course, I'm happy to talk offline in more detail. That is more than 1 minute of a Q&A session.
Some other question? Yeah.
Very beautiful application. I have a more technical question. So I'm not sure I see how you parallelize the computation. So you have to estimate first the number of segments you want, and then you're going to have you need to somehow dispatch a thread on the segment that's going to map on the curve. So how do you do this?
The question is exactly how do we map the computation to parallel threads? The current implementation is a fairly straightforward, is not a sophisticated application of parallelism. It is one thread per input segment. So you're really relying on the fact that you have tens of thousands, hundreds of thousands of input segments. And then in the current implementation, each thread is processing that using essentially a sequential computation. However, there is more parallelism. There is potentially a lot more parallelism that could be exploited. So just to give you a very quick outline of how that might be, the conversion from cubic Béziers to Euler spirals, that might be very difficult to subdivide because that error metric is complicated. You can't invert that. But once you get it to Euler spirals, like if you think about this as a work graph, you could think about the cubic to Euler as being one node in a work graph, and then that fills a buffer that is like the rate, the amplification factor might be dynamic, but work graphs can do that. So then once you generate those Euler spirals, then like the next node in the work graph might be able to do all of the Euler spirals for, all of the, I skipped a little fast. So you generate those Euler spirals, and then once you have the Euler spiral, you've got this simple scalar calculation that says how many arcs do I need to generate? And then you can do the amplification of that so that then in the next node in the work graph, each thread is actually outputting one arc. So there's potentially like even more parallelism. So that was the kind of first line of the future work here is how can you, but the results, I mean, you get interactive frame rates even with the existing. It's not a major blocker. This would just be a refinement that will let you get even more throughput on GPUs.
I guess in theory you can have some threads generated as well from some, I guess, balance.
To load balance, yeah. They're doing better load balancing would be like a further refinement.
Some other questions? If not, let's thank our speaker again and all other speakers.